We spent decades and $10 billion building the James Webb Space Telescope. The goal was simple: look back in time to the very beginning of the universe and confirm our theories. We thought we knew exactly what we would find. We expected to see a dark, empty void with a few small gas clouds just starting to turn into stars. But that is not what happened. As soon as the data started coming in, the astronomers realized something was wrong. Deep in the past, where there should be nothing but emptiness, the telescope found something that breaks the rules. It found a galaxy. And I don't mean a small collection of baby stars struggling to ignite. I mean a monster. A fully formed structure sitting in a time period where it has no right to exist yet. This is not a candidate. This is not a maybe. This is confirmed. The light has been analyzed. The chemistry has been verified. The math has been checked and rechecked. And the answer is impossible. Here is why that scares scientists. When we look at this galaxy, we are seeing it as it existed just a few 100 million years after the Big Bang. The universe at that point was practically a newborn. It should have been a ghost town, just hot gas, darkness, and silence. There wasn't supposed to be enough time in the history of reality for a structure like this to exist, but it does exist. This means one of two things. Either our equipment is lying to us, or the history of the universe is completely different from what we thought. You probably think you understand what it means when scientists say they found the oldest galaxy, but that is not how it works at all. Space and time are welded together. When you look at a distant object, you are not just seeing something far away, you are seeing something far back in time. Light takes time to travel. The light from the sun takes 8 minutes to reach your eyes. That means when you look at the sun, you are seeing it as it was 8 minutes ago. Now scale that up. The light from the nearest star beyond our sun takes 4 years to reach us. The light from the center of our galaxy takes 26,000 years. When astronomers look at distant galaxies, they are looking at light that has been traveling for billions of years. This means telescopes are time machines. They don't show you what the universe looks like now, they show you what it looked like then. The further you look, the further back you go. So when scientists talk about finding the oldest galaxy, what they really mean is this. They found the galaxy whose light has been traveling the longest. They found the light that started its journey closest to the moment of creation. This galaxy is not old in the sense that it has been sitting around for a long time. It is old in the sense that we are seeing it at an incredibly young age. We are seeing a baby photograph of a galaxy that might be a giant today, or might be dead, or might have been swallowed by something else. We have no idea what happened to it in the 13 billion years since the light we are seeing left its surface. We are ghosts looking at ghosts. But here is where it gets mathematically precise. Astronomers don't measure the age of distant galaxies with clocks or calendars. They measure it with color. When you move away from a source of sound, the pitch drops. This is called the Doppler effect. Light does the exact same thing. When a galaxy is moving away from us, the light stretches. It shifts toward the red end of the spectrum. We call this redshift. Astronomers use a number called Z to describe redshift. Z equals 0 means the object is not moving away from us at all. Z equals 1 means the light has been stretched by a factor of 2. The wavelengths have doubled. Z equals 6 means the light has been stretched by a factor of 7. When James Webb looks at the deepest parts of space, it finds galaxies with redshifts above 10, above 12, and now above 14. These are not just big numbers, these are timestamps. They are coordinates in the history of the universe. A galaxy at redshift 14 existed just 300 million years after the Big Bang. To put that in perspective, the universe is 13.8 billion years old. That means we are seeing this galaxy when the universe was only 2% of its current age. It is like looking at a photograph of a human being taken 2 weeks after conception. Now, you might be thinking, okay, so they found a distant galaxy. Why is that a crisis? The problem is not that it is distant. The problem is what it looks like. This is not a dim little smudge. This galaxy is bright, it is massive, and it is organized. It has structure, it has dust, it has heavy elements. These are the fingerprints of a mature system, and mature systems take time to build. But the math says there wasn't enough time. Let me explain how confirmation actually works. When James Webb takes a picture of the sky, it captures light from thousands of objects. The telescope doesn't just take a photograph, it takes a spectrum. It breaks the light apart into its component colors like a prism splitting sunlight into a rainbow. Inside that rainbow, there are dark lines. These lines are absorption features. They're the shadows of specific atoms that absorb specific wavelengths of light as it passed through the galaxy's atmosphere. Every element has a unique fingerprint. Hydrogen absorbs light at 100 to 21.6 nanometers. This is called the Lyman alpha line. When you look at the spectrum of a galaxy in a laboratory on Earth, these lines appear at specific known positions, but when the light is redshifted, the lines move. The whole spectrum gets stretched toward longer wavelengths. If you know where a hydrogen line should be in the lab, and you see it shifted to a longer wavelength in the telescope, you can calculate exactly how much the light has been stretched. This gives you the redshift. This gives you the distance. This gives you the age. And this is what confirmation means. It means they didn't just see a red blob and guess. It means they measured the spectrum. They found the lines. They identified multiple lines from different elements. They checked that all the lines were shifted by the same amount. They did the math, and the answer came back the same every time. This galaxy is real. The confirmation process is rigorous because the stakes are high. You cannot claim to have found the oldest galaxy in the universe based on a hunch. You need evidence. You need multiple independent lines of evidence. First, you need photometry. This is measuring the brightness of the galaxy through different filters. Each filter lets through a specific range of wavelengths. By comparing the brightness in different filters, you can estimate the redshift. This is called a photometric redshift. It is a first guess. It is fast and cheap, but it is not definitive. Sometimes the photometry is ambiguous. Sometimes a nearby dusty galaxy can mimic the colors of a distant galaxy. So, photometry gives you a target. It tells you which galaxies are worth following up. Then you need spectroscopy. This is where you actually measure the spectrum. You point the telescope at the galaxy and you collect light for hours or even days. You pass that light through a diffraction grating that spreads it into a rainbow. You measure the intensity at each wavelength. You look for the lines. This is harder than it sounds because distant galaxies are faint. The light is spread out over a wide range of wavelengths. The signal is weak. The noise is high. You need very sensitive detectors. You need long integration times. You need clear skies. Any contamination from foreground objects or cosmic rays can ruin the spectrum. So you take multiple exposures, you combine them, you clean the data, you fit models to the spectrum, you extract the redshift, and even then, you are not done. You need to check for consistency. Do the different emission lines agree? If you measure the redshift from the hydrogen line and the oxygen line, do you get the same answer? If not, something is wrong. Maybe one of the lines is contaminated. Maybe there is a blended feature from another object. You need to rule out all these possibilities. You need to make sure the lines you are seeing are real and not artifacts of the data processing. This is why confirmation takes time. This is why scientists are cautious about announcing new discoveries. They have been burned before by false positives. They have seen candidates that didn't hold up under scrutiny. So they are careful. They are methodical. They check everything twice. The galaxy we are talking about has been through this process. Multiple teams have looked at it. The spectroscopy is clean. The redshift has been measured to be above 14, which puts the galaxy at an age of less than 300 million years after the Big Bang. This is confirmed. To understand why that is a problem, you have to understand the timeline of creation. The Big Bang was not an explosion in space. It was an explosion of space. In the first fraction of a second, the universe was smaller than an atom. It was a boiling soup of energy so hot that matter couldn't even exist. As the universe expanded, it cooled. After about 380,000 years, it cooled enough for electrons to stick to protons and form the first hydrogen atoms. This is the moment we call recombination. Before this, the universe was opaque. Light couldn't travel. But after recombination, the fog cleared. The universe became transparent. This is the oldest light we can see. It is the cosmic microwave background. But even at this point, there were no stars, there were no galaxies. For the next few 100 million years, nothing happens. This is the cosmic dark ages. No stars, no light, just cold gas and gravity. Now imagine you're standing in that universe 380,000 years after the Big Bang. You look around. What do you see? Nothing. It is pitch black. The cosmic microwave background is there, but it is infrared. Your eyes can't see it. The universe is dark. The temperature is a few thousand degrees, which sounds hot, but it is not hot enough to glow visibly. As the universe expands further, it cools further. The temperature drops. The darkness deepens. For the next few 100 million years, nothing happens. This is the cosmic dark ages. No stars, no light, just cold gas and gravity. Gravity is a slow process. It takes millions of years for tiny fluctuations in the density of gas to pull matter together. The denser regions had slightly stronger gravity. They started pulling in gas from their surroundings. As gas fell in, the region got denser. This is a runaway process, but it is slow. Eventually, the cores of these clouds got hot enough to ignite nuclear fusion. This is how the first stars were born. We call them population 3 stars. They were massive, they were bright, they were made of pure hydrogen and helium because no other elements existed yet. These first stars were the foundries of the universe. In their cores, hydrogen fused into helium, helium into carbon, carbon into oxygen. The fusion chain continued all the way up to iron, but fusion stops at iron. The star runs out of fuel, the core collapses, and then it explodes. This is a supernova. When a population 3 star exploded, it scattered the newly made elements into space: carbon, oxygen, silicon, iron, all the ingredients for rocky planets and biological life. The next generation of stars formed from this enriched gas. Generation after generation, the universe got more chemically complex, but stars are not galaxies. A galaxy requires thousands or millions of stars bound together by gravity. It requires dark matter, halos, to anchor the structure. It requires time for gas to cool and settle into rotating disks. It requires generations of stars to be born, live, and die to enrich the gas with metals. The textbook timeline says this process takes hundreds of millions of years, at minimum. Think of it like building a city. First you need people, then you need houses, then you need roads. A city doesn't appear overnight. It grows organically over decades or centuries. Galaxies form the same way. Small clumps of stars merge to make bigger clumps. This cycle repeats. Over billions of years, the galaxy grows. So when James Webb finds a galaxy at 300 million years that is already massive, already bright, and already full of dust and metals, the timeline is broken. It is like walking into a construction site on the first day and finding a finished skyscraper already standing there. The building materials were only delivered yesterday. There is no physical way the structure could be completed, but it is completed. Let me tell you what this galaxy looks like on paper, because the numbers are obscene. The observed brightness suggests it is producing stars at a rate that would build the equivalent of our entire sun every single year. Our Milky Way galaxy produces about 1 solar mass of new stars per year. This ancient monster is matching that output when it should barely be flickering into existence. The estimated stellar mass is somewhere in the range of 1 billion solar masses, and it gets worse. This galaxy shows signs of dust. Dust is made of heavy elements: carbon grains, silicate particles. These things are not produced by the Big Bang. They're produced inside stars. A star has to form, burn for millions of years, and then die in a supernova explosion to scatter those elements into space. Only then can those elements condense into dust grains. This is a generational process, but this galaxy already has dust when the universe is barely old enough to have grandparents, let alone great-grandparents. The presence of dust tells us that not only have stars lived and died, but the conditions were right for dust to form and survive. This implies that the galaxy had dense regions where the gas could cool efficiently. It implies a level of chemical and physical maturity that we didn't expect to see so early. On top of that, spectroscopic observations show emission lines from ionized oxygen. This is another metal. The presence of oxygen means that massive stars have already lived and died in this system. But those stars take time to evolve. A star 25 times the mass of the Sun will live for about 6 million years before it explodes. A star 10 times the mass of the Sun lives for about 20 million years. These are the stars that make oxygen. They burn fast, but they don't burn instantly. If you need multiple generations of stars to build up the oxygen abundance we are seeing, you are eating into your budget of time very quickly. There are only 300 million years total to work with. Every million years spent waiting for stars to evolve is a million years you can't use for something else. Let me give you a concrete example of the time budget. Suppose the very first star in this galaxy formed 250 million years after the Big Bang. That gives you 50 million years of star formation history before the moment we observe the galaxy at 300 million years. That sounds like a lot, but it is not. The first generation of stars has to form, evolve, and explode. Let's say the first stars are very massive, 50 to 100 solar masses. They live for only a few million years. They explode and enrich the gas. Now you have gas with a tiny bit of metals. The second generation of stars forms from this enriched gas. These stars are smaller on average because the gas can cool more efficiently now. They live longer. Let's say the average lifetime of second-generation stars is 10 million years. Some of them explode and add more metals. Now you have more enrichment. The third generation forms, and so on. By the time you get to the moment we observe, at 300 million years, you might have had 3 or 4 generations of stars. Maybe 5 if you push the efficiency very high. Each generation adds more metals, but you also have to account for the time it takes for gas to cool and collapse between generations. You have to account for the fact that supernova explosions heat the gas and blow it out of the galaxy. It takes time for that gas to fall back in. You have to account for the fact that not all the gas turns into stars. Most of it stays as gas. Only a small fraction, maybe a few percent, actually form stars in each episode. When you add all this up, you start to run out of time. You can barely fit the required number of generations into 50 million years, let alone build up a billion solar masses of stars. And remember, this is assuming that star formation started at 250 million years. But that is already very early. The conventional wisdom is that the first stars didn't form until at least 100 million years after the Big Bang, maybe 150 million years. If star formation in this galaxy didn't start until 200 million years, then you only have 100 million years of history. That makes the problem even worse. You have even less time to build the mass and enrich the gas and form the dust. Some observations also suggest that this galaxy might have structure. It might not be a chaotic blob. It might have a disk or a concentration of stars in the center. Structure implies organization. Organization implies time. In the early universe, gas clouds are turbulent. They are messy. They collide and merge violently. When two gas clouds collide, they shock. The gas heats up. The shock dissipates energy. Eventually, the gas cools and settles, but this takes time. For a rotating disk to form, the gas has to lose its random motions and settle into a plane. This happens through a process called dynamical relaxation. Particles collide and exchange energy. Over time, the system reaches a state where everything is rotating in the same direction. This is equilibrium, but equilibrium is not instant. It takes many orbital periods. It takes tens or hundreds of millions of years. The fact that we might be seeing organized structure this early is another red flag. It is another piece of evidence that the galaxy is more mature than it has any right to be. If the galaxy has a disk, it means the gas has already settled. If it has a bulge, it means there has been enough time for stars to migrate inward and build up a central concentration. If it has spiral arms, it means the disk is gravitationally unstable and density waves are propagating through it. All of these features require time to develop. They require a galaxy that has been evolving for a significant fraction of its lifetime. But this galaxy's lifetime is only 300 million years. That is not a significant fraction of cosmic time. That is barely a blip. So why is this impossible? What is the actual bottleneck? Let me walk you through the physics, because this is where the trap closes. The first problem is cooling. When a cloud of gas collapses under gravity, it heats up. This is basic thermodynamics. Compression increases temperature. The gas molecules are moving faster. They collide more frequently. The kinetic energy goes up. For the gas to continue collapsing and form stars, it has to get rid of that heat. It has to cool down. If the gas stays hot, the pressure resists gravity. The collapse stalls. No stars form. The way gas cools is by radiating energy away. Atoms collide with each other, and when they collide, they emit photons. Those photons carry energy out of the cloud. The cloud loses heat. It contracts further. This is how star formation happens. But here is the catch. The efficiency of cooling depends on what the gas is made of. Hydrogen and helium are terrible at cooling. They don't radiate energy efficiently unless the gas is extremely dense or extremely hot. The reason is quantum mechanics. Hydrogen has a very simple electronic structure. It only has one electron. The energy levels are widely spaced. To excite the electron and emit a photon, you need a collision with enough energy to bridge the gap between levels. In a low-density, low-temperature gas, most collisions don't have enough energy. The cooling is inefficient. Heavy elements like carbon and oxygen are much better coolants. They have more complex electronic structures. They have many closely spaced energy levels. Even low-energy collisions can excite them. They radiate energy at lower temperatures. This means that a gas cloud with metals in it can cool faster and collapse faster than a pure hydrogen cloud. The presence of metals dramatically increases the cooling rate. In some cases, it can increase it by a factor of 10 or more. This is one of the reasons why star formation is more efficient in the later universe. The gas has been enriched with metals from previous generations of stars. It cools faster, it forms stars more easily, but in the early universe there are no metals. The first gas clouds are pure hydrogen and helium, plus a tiny trace of lithium that was made in the Big Bang. This means they cool slowly. This means star formation should be slow. This is one of the fundamental speed limits on galaxy formation. You can try to get around this by making the gas denser, but density is also limited. The amount of gas in a given region is set by the overall density of the universe at that time, which is determined by cosmology. You can't just wish more gas into existence. You are working with the hand you were dealt. And the hand is not very good in the early universe because the universe is still relatively uniform. The density fluctuations that seed galaxy formation are small. It takes time for gravity to amplify them into the deep potential wells where galaxies can form. There is a subtle but important point here. The cooling problem is self-regulating. When the first generation of stars forms and dies, they enrich the gas with metals. Now the gas can cool faster. The second generation of stars forms more easily. They enrich the gas further. The third generation forms even more easily. This is a positive feedback loop. The more stars you make, the easier it becomes to make more stars. But you still need to get the process started. You still need the first generation of stars to form in a metal-free environment. And that first generation is slow and inefficient. This is the bottleneck. Once you get past the bottleneck, things speed up. But getting past the bottleneck takes time that the early universe doesn't have in abundance. The second bottleneck is feedback. This is a word that sounds technical, but the concept is simple. When stars form, they don't just sit there quietly burning. They blast energy into their surroundings. Massive stars produce intense, ultraviolet radiation. This radiation heats the nearby gas and ionizes it. When a hydrogen atom is ionized, the electron is stripped away. The atom becomes a proton. Ionized gas is hotter than neutral gas. Hot gas has higher pressure. Higher pressure resists gravity. This makes it harder for the gas to collapse and form more stars. So star formation creates its own resistance. The radiation from young stars heats the gas and prevents more stars from forming. This is called radiative feedback. But it gets worse. When massive stars die, they explode as supernovae. These explosions release more energy than the star emitted during its entire lifetime. A single supernova releases about 10 to the 51 ergs of energy. That is one followed by 51 zeros. It is an absurd amount of energy. When that energy is dumped into the surrounding gas, it creates a shock wave. The shock wave accelerates the gas to thousands of kilometers per second. The gas is blown out of the galaxy entirely. This is called a galactic wind. Once the gas is gone, star formation stops. You can't make stars without gas. The galaxy has to wait for the gas to cool and fall back in before it can start forming stars again. But in a shallow, gravitational potential, the gas might not fall back in at all. It might escape to intergalactic space and be lost forever. This creates a self-regulating cycle. Star formation heats and expels gas. Expelling gas shuts down star formation. The galaxy has to wait for new gas to accrete from its surroundings. This cycle limits how fast a galaxy can grow. If you form stars too efficiently, you destroy your own fuel supply. This is why modern galaxies don't turn 100% of their gas into stars. They are inefficient by design. The efficiency is limited by feedback. Typical star formation efficiencies in modern galaxies are only a few percent. Most of the gas never turns into stars, it just sits there, or it gets expelled. But the galaxy we are seeing is massive. It has already converted a huge amount of gas into stars. If feedback was working the way we think it should, this galaxy should have blown itself apart. The supernovae from the first generation of stars should have expelled the gas and shut down star formation before the second generation could even begin. But clearly that didn't happen. So either feedback was weaker in the early universe, or something was suppressing it. One possibility is that the gas was so dense that even supernova explosions couldn't clear it out. In a very dense environment, the gas has a lot of inertia. It is hard to accelerate. The shock wave from a supernova might compress the gas and trigger more star formation instead of expelling it. This is called positive feedback. It is the opposite of what we usually expect. Instead of shutting down star formation, the supernovae trigger more of it. This can happen, but it requires very specific conditions. The gas density has to be just right. Too low, and the shockwave blows the gas out. Too high, and the gas cools so fast that the shockwave dissipates before it can do anything. The window where positive feedback dominates is narrow. Another possibility is that the dark matter halo was so deep that the gas couldn't escape, no matter how much energy was pumped into it. A deeper halo has a higher escape velocity. To blow gas out of the halo, the shockwave has to accelerate the gas faster than the escape velocity. If the escape velocity is very high, this is hard to do. The gas gets heated and expelled from the inner regions, but it doesn't escape the halo. It just piles up in the outer regions and eventually falls back in. This is called a fountain flow. The gas goes up and comes back down. Star formation continues in a bursty mode, with each burst triggering a fountain that feeds the next burst. These are possibilities, but they require fine-tuning. They require the galaxy to be sitting in a very special environment. And if every early massive galaxy requires special conditions, then you start to run into a statistical problem. How many special environments can you have? If massive galaxies are supposed to be rare because they require rare conditions, then finding even one is a lucky break. Finding two is suspicious. Finding 10 is a crisis. And the early data from James Webb suggests there might be more than one. There are multiple candidates at high redshift with large estimated masses. Not all of them have been confirmed spectroscopically yet, but the trend is troubling. The abundance might be higher than predicted. The third bottleneck is halo assembly. Galaxies don't form in isolation. They form inside dark matter halos. Dark matter is the invisible scaffolding that holds the universe together. It doesn't interact with light, but it does interact with gravity. In the early universe, dark matter started clumping together first because it doesn't feel pressure or radiation. It just feels gravity. Normal matter, the hydrogen and helium gas, feels pressure. It resists collapse, but dark matter doesn't. It collapses freely. These clumps grew over time, merging with each other and pulling in normal matter. The normal matter falls into the dark matter halo and collects at the center. This is where stars form. This is where galaxies are born. But halo growth has its own speed limit. In the standard model of cosmology, structure forms hierarchically. Small halos form first. They merge to make bigger halos. Those merge to make even bigger halos. It is a bottom-up process. This is not arbitrary. It is a direct consequence of the initial conditions set up at the Big Bang. The density fluctuations in the early universe had a specific pattern. Small-scale fluctuations had higher amplitude than large-scale fluctuations. This means small structures collapse first. Large structures took longer because they had to wait for many small structures to merge. At very early times, there simply haven't been enough mergers yet to build the massive halos required to host a massive galaxy. The math of structure formation is well understood. You start with the power spectrum of density fluctuations, which we measure from the cosmic microwave background. You evolve that forward in time using the equations of gravitational collapse. You calculate how many halos of each mass exist at each redshift. This gives you a halo mass function. The halo mass function is steep. There are many more small halos than large halos, and the steepness increases at high redshift. At redshift 14, halos above a certain mass threshold are exponentially rare. They are statistical outliers. Finding one is unlikely. Finding many of them would be a crisis. The mass of the halo determines how much gas it can hold. A more massive halo has a deeper gravitational well. It can pull in more gas from its surroundings. It can hold onto that gas even when supernovae try to blow it out. The escape velocity from a massive halo is high. To blow gas out, you need to give it enough energy to overcome the gravitational binding energy. If the halo is very massive, that binding energy is very large. The feedback has to be very strong to expel the gas. This is why massive galaxies can form stars more efficiently than small galaxies. They have deeper potential wells. They are harder to disrupt. But if the halo itself hasn't had time to assemble, then there is no deep well to begin with. The gas has nowhere to collect. This is the chicken and egg problem. You need a massive halo to build a massive galaxy, but you need time to build a massive halo, and there isn't enough time. The only way out is if the halo formed in an unusually dense region where the collapse happened faster than average. But again, that is invoking special conditions. You are saying the galaxy is rare, and if galaxies are rare, you shouldn't find many of them. Let me be very clear about what the standard model predicts. The Lambda-CDM model, which stands for Lambda Cold Dark Matter, is the backbone of modern cosmology. Lambda is the cosmological constant, which represents dark energy. CDM is cold dark matter, which clumps gravitationally to form structure. This model describes how the universe expands and how structure forms. It has been tested extensively and it works. It explains the cosmic microwave background. It explains the distribution of galaxies in the modern universe. It explains the patterns we see in large-scale surveys. It explains the clustering of matter on scales, from kiloparsecs to gigaparsecs. It is a successful theory, but it makes very specific predictions about the early universe. It says that at redshift 14, massive galaxies should be rare. Not impossible, but rare. Maybe 1 in a million regions of space. The numbers depend on exactly how you define massive, but the trend is clear. The higher the redshift and the higher the mass, the rarer the object. If James Webb looks at a small patch of sky and finds one massive galaxy, that is fine. It is a lucky find. The patch happened to contain one of those rare regions, but if it finds 5 or 10 or 20, then the statistics are wrong. The model is underpredicting the abundance of massive early galaxies. And if the model is wrong about abundance, it might be wrong about other things too. This is the edge we are walking right now. One confirmed massive galaxy at extreme redshift is interesting. It is a challenge. It forces us to think harder about star formation efficiency and halo assembly. But it is not necessarily a crisis. It could just be a rare object that formed in an unusually dense region. We can adjust the parameters slightly and accommodate it. However, if this is not a one-off, if this is the beginning of a pattern, then we have a problem. And the early data from James Webb suggests it might be a pattern. There are multiple candidates. Not all of them have been confirmed yet, but the trend is troubling. The universe seems to have been more active in its first few 100 million years than we gave it credit for. So let us talk about the explanations that don't require us to rewrite physics. The first way to be fooled is by photometric redshift. Sometimes, a nearby dusty galaxy can look red enough to mimic a distant galaxy. But the galaxy we are talking about has been confirmed spectroscopically. The spectrum has been measured by James Webb's NIR SPEC instrument. The lines have been detected with high signal-to-noise ratio. The redshift is real. The second way to be fooled is by gravitational lensing. If there is a massive object sitting between us and the distant galaxy, the gravity can bend the light and magnify the background galaxy. As far as we know, the galaxy in question is not strongly lensed. But even with a magnification factor of 2, the galaxy is still too massive for its age. The third way to be fooled is by misinterpreting the light. Active galactic nuclei, powered by supermassive black holes, can be incredibly bright. If you mistake the light from a black hole for the light from stars, you will overestimate the stellar mass. But there are galaxies where the spectral signatures clearly indicate star formation, not black hole activity. The fourth way to be fooled is by dust. Dust makes galaxies look redder and older. But even with conservative assumptions, even with the maximum plausible amount of dust, the galaxy is still too massive. So if we are not being fooled, what is the astrophysical explanation? How do you build a massive galaxy in 300 million years without breaking the laws of physics? The first possibility is that star formation was simply more efficient in the early universe than we thought. Efficiency here means the fraction of gas that gets turned into stars per unit time. In the modern universe, star formation is inefficient. Only a few % of the available gas turns into stars before feedback shuts it down. The rest of the gas is either expelled by winds or it just sits there unconsumed. But maybe in the early universe, before feedback had time to develop, before the first supernovae exploded, there was a brief window where star formation could proceed at much higher efficiency. Maybe the gas was so dense and so cold that it collapsed rapidly into stars before anything could stop it. Maybe the turbulence in the gas was low, allowing smooth, efficient collapse. Maybe the magnetic fields were weak, offering no resistance. This is the starburst scenario. It is a short, violent burst of star formation that produces a huge mass of stars in a very short time. Starbursts are seen in the modern universe. They happen when galaxies collide and merge. The collision funnels gas into the center of the system. The gas pileup triggers intense star formation. Star formation rates can reach hundreds of solar masses per year, far higher than normal. The starburst lasts for a few tens of millions of years, and then it burns out. The gas is exhausted or expelled, and star formation drops to normal levels. If something similar happened in the early universe, you could potentially build a massive galaxy in a short time. The problem with this scenario is that it still requires the gas to be there in the first place. You can't turn gas into stars if you don't have gas. Where did all the gas come from? It had to fall into the dark matter halo. The halo had to assemble early. This brings us back to the halo assembly problem. But maybe the solution is that the halo did assemble early because it formed in a special region. In the early universe, the distribution of matter is not perfectly uniform. There are small fluctuations, regions that are slightly denser than average. These regions are called overdensities. They collapse faster because they have stronger gravity. They pull in material from a larger volume. They form halos earlier than average regions. If the galaxy formed in a rare overdensity, a peak in the density field, then it could have assembled its halo faster than average. It could have pulled in gas faster than average. It could have started forming stars earlier than average. This is a valid explanation, but it comes with a statistical cost. Rare objects are, by definition, rare. If you invoke a rare overdensity to explain one object, that is fine. The universe is big. Somewhere out there is a rare region, but if you need to invoke rare overdensities to explain many objects, you run into a probability problem. How rare is rare? If 1 in a million regions is overdense enough to form a massive galaxy by redshift 14, and you observe a survey volume that contains 1 million such regions, you should find one massive galaxy. But if you find 10, you have a problem. Either the overdensities are not as rare as you thought, which means your model of the initial conditions is wrong, or the efficiency boost in those regions is larger than you thought, which means your model of star formation is wrong. Either way, something has to change. Another astrophysical explanation involves the stellar initial mass function, or IF. This is the distribution of masses for newly formed stars. In the modern universe, when a gas cloud collapses and fragments into stars, most of the stars are small. Low-mass stars, red dwarfs. These stars are faint and they burn slowly. They live for billions of years. Only a small fraction of stars are massive. Blue giants. These stars are bright and they burn fast. They live for only a few million years. The ratio of low mass to high mass stars is called the IMF, and it has a specific shape that we observe in nearby star-forming regions. This shape is called the Salpeter IMF, or the Krupa IMF, depending on the exact functional form. But maybe in the early universe, the IMF was different. Maybe the first stars were predominantly massive. This is called a top-heavy IMF. The reasoning is that in the absence of metals, the gas can't cool as efficiently. Without efficient cooling, the gas can't fragment into small pieces. The gene's mass, which is the minimum mass for gravitational collapse, is higher, so the fragments that do collapse are more massive. They form massive stars instead of a mix of massive and low-mass stars. A top-heavy IMF changes everything. Massive stars are brighter, so the galaxy looks brighter for a given mass of stars. If all your stars are 10 times the mass of the Sun, instead of a mix that includes many 0.1 solar mass stars, the total luminosity is much higher. Massive stars produce more heavy elements, so the chemical enrichment happens faster. A single 50 solar mass star produces more oxygen and carbon in its lifetime than 101 solar mass stars. Massive stars die faster, so the feedback is more intense, but also more concentrated in time. If all your stars die within 10 million years, you get a huge burst of supernova energy all at once. This could blow the gas out more effectively, or if the halo is deep enough, it could just heat the gas and trigger another burst of star formation. If the early universe had a top-heavy IMF, you could potentially form a massive, bright, metal-rich galaxy in less time than you could with a normal IMF. The catch is that we don't have direct evidence for a top-heavy IMF. We can't resolve individual stars in these distant galaxies. We can only infer the IMF from the integrated light, and that inference depends on models and assumptions. You measure the total luminosity and the colors. You fit a model that includes stars of different masses. You adjust the IMF until the model matches the observations. But the fit is degenerate. Many different combinations of age, metallicity, and IMF can produce the same observed spectrum. Breaking the degeneracy requires additional information, like measuring the supernova rate or detecting specific spectral features that are sensitive to the IMF. This is technically challenging. There is some theoretical support for a top-heavy IMF in metal-free gas, but the evidence is not conclusive. Simulations of the first stars suggest they were massive, but those simulations are uncertain. They depend on the details of how the gas cools in fragments, which depend on the chemistry and the radiation field, which are hard to model accurately. So a top-heavy IMF is possible, but it is not proven. It is an explanation that fits the data, but it is not the only explanation. There is also the possibility that black holes play a role, not as contaminants that make the galaxy look brighter than it is, but as catalysts that accelerate the assembly process. Supermassive black holes can form very early in the history of the universe. We see quasars, which are powered by black holes, at redshifts above 7. Some quasars have been found at redshift above 7.5, which corresponds to an age of less than 700 million years. These black holes have masses of billions of suns, and they somehow assembled in the first billion years of cosmic history. How did they get so massive so fast? This is its own puzzle, and it is related to the massive galaxy puzzle. Black holes grow by accreting gas. The gas spirals into the black hole and releases energy. The rate of accretion is limited by the Eddington limit, which is the maximum rate at which a black hole can accrete before the radiation pressure from the infalling gas blows away the remaining gas. If a black hole accretes at the Eddington limit, it can double its mass in about 50 million years. Starting from a seed black hole of, say, 100 solar masses, you can grow to 1 billion solar masses in about 500 million years if you accrete continuously at the Eddington limit. But that is a big if. Continuous accretion is hard to maintain. Gas has angular momentum. It wants to orbit the black hole, not fall in. To fall in, the gas has to lose angular momentum, which requires viscosity or magnetic torques or some other mechanism to transport angular momentum outward. And even if the gas does fall in, the radiation from the accretion disk can heat the surrounding gas and prevent more gas from falling in. This is feedback again. The black hole regulates its own growth. So getting 1 billion solar mass black hole by 700 million years is hard, but not impossible. You need efficient accretion, and you need to start with a reasonably massive seed, and once the black hole is there, it can influence the galaxy. If a black hole forms early in the center of a galaxy, it can influence the surrounding gas in complex ways. It can heat the gas and prevent it from forming stars, which is negative feedback. This is what we see in massive galaxies in the local universe. The AGN turns on, heats the gas, and shuts down star formation. The galaxy becomes red and dead, but the black hole can also compress the gas and trigger star formation, which is positive feedback. The radiation from the AGN creates a pressure wave that propagates through the gas. The wave compresses the gas ahead of it. If the compression is strong enough, the gas can collapse and form stars. In some scenarios, the black hole and the galaxy grow together in a symbiotic relationship. The black hole pulls in gas, radiates energy, and that energy compresses nearby clouds, which form stars, which produce more gas and metals, which feed the black hole. It is a runaway process that can accelerate the growth of both the black hole and the galaxy. This is an active area of research, and the jury is still out. We don't know exactly how the first black holes formed. We don't know how they grew so fast. The existence of early quasars is itself a puzzle that is related to the massive galaxy puzzle. They might be two sides of the same coin. If we solve one, we might solve the other. But right now, we don't have a clear answer. We have hints from simulations and observations, but we don't have a complete picture. Now let us talk about the scenario that makes physicists nervous. What if the observations hold up and the explanations don't work? What if we confirm 10 or 20 massive galaxies at redshift above 14 and none of the astrophysical fixes can account for them? Then we have to consider the possibility of new physics. New physics means modifying the fundamental assumptions of the cosmological model. It could mean changing the properties of dark matter. Maybe dark matter is not cold. Maybe dark matter is warm or self-interacting. It could mean changing the nature of dark energy. It could mean modifying gravity itself. These are not casual suggestions. These are radical changes that would have consequences for everything else we observe. If you change the properties of dark matter to make early galaxies form faster, you have to check that it doesn't break the fit to the other observations. There is one proposal that has gained some attention. It involves early dark energy, a form of energy that was present in the very early universe but decayed away later. This early dark energy could have slowed down the expansion temporarily, giving structures more time to collapse and grow. But it is not a perfect fix. It is designed to fit the data rather than being derived from fundamental principles. The important point is this: if the data forces us to invoke new physics, it will not be because of one galaxy. It will be because of a population of galaxies. 1 or 2 objects can be accommodated, but 10 or 20 objects cannot. If the abundance is high, you need a systematic change to the model. So the next few years of observations are critical. James Webb is going to keep looking. The sample size will grow. The statistics will improve, and we will know whether the oldest confirmed galaxy is a rare oddball or the tip of an iceberg. How do scientists plan to test this? What are the next steps? The first step is better spectroscopy. The initial confirmation of the galaxy was based on detecting a few key emission lines. The spectrum was noisy. The signal-to-noise ratio was just high enough to identify the lines and measure the redshift. But to really understand the galaxy, you need a full spectrum with high signal-to-noise ratio. You need to measure multiple lines from different elements. You need to measure the line widths, which tell you about the velocity of the gas. Narrow lines indicate slow gas motion, which means the gas is in a disk or a halo. Broad lines indicate fast gas motion, which might mean there is an AGN or a galactic wind. You need to measure the line ratios, which tell you about the temperature and density of the gas and the hardness of the radiation field. All of this requires deeper observations with longer integration times. James Webb is already scheduling follow-up programs to do exactly this. The goal is to build a detailed physical model of the galaxy. Not just how massive it is, but how it is structured, how it is forming stars, what is ionizing the gas, and what is powering the emission. This is time-consuming work. Each spectrum might require 10 or 20 hours of telescope time, but it is necessary to answer the fundamental questions. The second step is to check for lensing more carefully. Even if the galaxy is not obviously lensed, there could be a weak lensing, magnification that is hard to detect. The way to check this is to map the environment around the galaxy. Are there other galaxies nearby at similar redshifts? Is there a cluster of galaxies in the foreground? You need wide-field imaging and spectroscopy of the surrounding area. You need to map the three-dimensional structure. You need to identify which galaxies are at the same redshift as the target galaxy and which are in the foreground. If there is a foreground structure, you can model its mass using lensing or dynamics. You can calculate the expected magnification. You can correct for it. This is a lot of work, but it is necessary to rule out systematic errors. The third step is deep imaging to measure the true size and shape of the galaxy. The initial detections were made in survey mode, where the goal is to cover a large area of sky, but with limited depth. The exposure time per field is short. You can see the brightest objects, but you miss the faint extended emission. To really see the structure of the galaxy, you need to integrate for a long time on a small area. You need to push down to the faintest possible surface brightness. This will reveal whether the galaxy has a disk, a bulge, or clumps of star formation. It will reveal whether the mass is concentrated in the center or spread out. Morphology is a key diagnostic. A smooth elliptical galaxy looks different from a clumpy, irregular galaxy, and the difference tells you something about the formation history. A smooth galaxy suggests a relaxed system that has had time to settle. A clumpy galaxy suggests recent mergers or intense star formation that has not yet smoothed out. A disk suggests organized rotation, which requires time to develop. A spheroid suggests violent relaxation through mergers. These different morphologies point to different formation scenarios. Imaging can also reveal tidal tails or bridges, which are signatures of recent interactions with other galaxies. The fourth step is to compare populations. Is this galaxy a freak outlier, or is it the tip of an iceberg? Are there other galaxies at similar redshifts with similar masses? Are there galaxies at slightly lower redshifts that are even more massive? If you can build a mass function, a histogram of galaxy masses at each redshift, you can compare it to the predictions of the model. The shape of the mass function is sensitive to the underlying cosmology and the physics of galaxy formation. A steep mass function means there are many low-mass galaxies and few high-mass galaxies. A shallow mass function means the ratio is less extreme. The slope tells you about the efficiency of galaxy formation as a function of halo mass. If the observed mass function is steeper than predicted, it means massive galaxies are more common than expected. If it is shallower, it means they are rarer. Right now, the sample size is too small to build a reliable mass function. But as more galaxies are confirmed, the sample will grow and the statistics will improve. Within a few years, we should have enough data to make quantitative comparisons. One of the key tests is the dust. Dust is made of heavy elements, and heavy elements come from stars. In principle, you can measure the dust mass from infrared observations. James Webb has infrared cameras that are perfect for this. If you can measure the dust mass and compare it to the stellar mass, you get a dust-to-stars ratio. Another test involves the chemical composition. Spectroscopy can measure the abundances of specific elements like oxygen, carbon, and nitrogen. By measuring the ratios of these elements, you can infer the star formation history. This requires very high-quality spectra with many detected lines. There is also the possibility of finding molecular gas. Stars form from molecular hydrogen. If you can detect the molecular gas in a distant galaxy, you can measure the fuel supply. The Atacama Large Millimeter Array, ALMA, is capable of doing this. Another angle is to look for companion galaxies. Galaxies grow by merging. If the massive galaxy we are seeing is the product of a recent merger, there might be remnants visible. The presence or absence of companions tells you something about the assembly history. The broader takeaway is that the first billion years of cosmic history were more eventful than we thought. We used to think of the early universe as a slow, gradual process, but James Webb is showing us that the universe woke up fast. Structure formed early. Galaxies assembled early. Whether this is due to astrophysics we didn't fully appreciate, or whether it requires new physics, is still an open question. The reason we say this galaxy shouldn't be possible is not because it violates the laws of physics in some fundamental way. What the galaxy violates is our assumptions about how efficiently and how quickly these processes can happen in the early universe. We assume that feedback would be strong. We assume that cooling would be slow. We assume that halo assembly would be gradual. But assumptions are not laws. Assumptions can be wrong. This is actually a common theme in the history of astronomy. Every time we build a new telescope that can see further or more clearly, we find something that surprises us. When the Hubble Space Telescope first looked at the deep field in 1995, it found galaxies at redshifts that were thought to be impossible. When sub-millimeter telescopes found dusty star-forming galaxies in the early universe, it was a surprise. When Hubble found quasars at redshift above 6, it was a surprise. The models had to be adjusted. The universe is always more complex than our theories. When we find something unexpected, it is not a failure of science. It is an opportunity. It is a chance to refine our models and improve our understanding. What we are learning from the oldest confirmed galaxy is that the details of early galaxy formation are more complicated than we thought. The interplay between gas cooling, star formation, feedback, halo assembly, and chemical enrichment is a messy, non-linear process. Small changes in initial conditions can lead to large changes in outcomes. But there is a limit to how much you can vary the parameters before the model becomes implausible. If you have to invoke optimal conditions to explain every massive early galaxy, then the lottery is rigged. This is where the tension lies. We can accommodate one or two outliers. We cannot accommodate a population of outliers. So here's where we stand. We have confirmed the existence of at least one massive galaxy at redshift above 14. The confirmation is solid. This is unexpected based on the standard timeline of galaxy formation. There are astrophysical explanations that can potentially account for it, but they require the galaxy to be special. The next step is to determine whether this galaxy is special or whether it is representative. If there are many more like it, then the standard model is under-predicting the abundance, and we need to understand why. The beauty of this situation is that we now have the tools to answer these questions. James Webb was built for exactly this purpose. Within the next few years, we will have a much clearer picture of the early universe. And that picture might not be what we expected. It might be more complex, it might have bursts and lulls, it might reveal new physics, or it might just reveal that the known physics operates in more varied ways than we appreciated. Either outcome is progress. This is how science works. You make a prediction, you test it. If the test disagrees, you learn something new. The oldest confirmed galaxy is a test that disagrees with some of our predictions. That disagreement is valuable. It is telling us where our models are weak. You have to understand that this is not a crisis of confidence. This is excitement. This is what astronomers live for, the chance to discover something unexpected. When we find something we can't immediately explain, we don't throw up our hands. We double down, we take more data, we refine our models. The oldest confirmed galaxy is a monument to the unexpected. It is standing in a time and place where our models said it shouldn't be. And we will figure it out. We will measure it from every angle. We will model it with increasing sophistication. We will test every hypothesis. And when we finally understand how this galaxy formed, we will have learned something profound about the birth of structure in the universe. We will have a better understanding of how gas cools and collapses. We will have a better understanding of how stars form in extreme environments. We will have a better understanding of the timeline of cosmic history. That is the promise. That is the challenge. And that is why we build telescopes in the first place. To see what we have never seen. To find what we didn't expect. This galaxy is proof of that. It is a reminder that reality does not care about our assumptions. The oldest galaxy is showing us that we still have a lot to learn. And that is not a problem. That is an opportunity.